collect a sample, compute the sample mean, and try to use that sample mean together with the central limit theorem to construct a confidence interval for the population mean. That's what I'm trying to do here. Okay. So let's take a look at the example that I wanted to start with to give us a picture for how this might work. Administrators of a hospital in Nashville are concerned about the prenatal care given to mothers in their part of the city. They drew a random sample of 70 babies born in their hospital in the last 6 months and analyzed the gestation times. We know that human gestation times for normal pregnancies can be modeled by a normal distribution with a mean of 280 days and a standard deviation of 14 days. In their sample, the mean gestation time was 275 days. Can they construct a confidence interval for their hospital's mean to compare to the standard 280 and 14? Well, they can, but the question is, how do we do it? Now let's think back to what we did with the case of proportions. We took the sample proportion we observed, and we treated that as the midpoint of our confidence interval. Then we computed a margin of error to tell us how far above or below that to go to get the desired confidence level that we are capturing the true value somewhere in that window. Okay. Well, here, if we want a 95% confidence interval, what we're going to do is construct a margin of error built on 1.96 standard deviations above the mean and below the mean to feel 95% confident that we've captured the true value. The difference is we have to think about what the standard error for the mean is, and that's it. That's actually all we have to do here. So let's think back. In the case of proportions, for 95% confidence, I use z star equals 1.96, and I use my standard error as the square root of p hat times q hat over n, and then my margin of error was z star times the standard error. Okay. My confidence interval from that was whatever I observed in the sample plus or minus the margin of error. A lot of writing here, but it's the same idea. I'm taking my estimate from the sample as the midpoint, and then I'm adding the margin of error above it, or subtracting the margin of error below it, and computing the margin of error is easy. It's the critical value times the standard error. Okay. What about for means? If I want to compute a confidence interval for a population mean, I'm going to start with a sample mean as my point estimate. I need to decide what critical value to use if I want 95% confidence. It's still going to be the 1.96. The standard error for the mean, in fact the way I should do this is standard error of x bar, is sigma over the square root of n. Right, we learned this before when we talked about sampling variability. If I know the population standard deviation, I can simply scale it down by the square root of the sample size to get the sampling variation, the sampling standard deviation. And then I construct the margin of error using a very similar formula. I take this critical value times the standard error, which in this case is sigma over the square root of n, and then my confidence interval is the midpoint, which is the sample mean in this case, plus or minus the margin of error. And so this is exactly the same idea, but instead of computing a sample proportion, and then the standard error for proportions comes from this formula, I'm computing a sample mean, and then the standard error for means comes from this formula. Otherwise, I'm doing exactly the same thing as I did before. I still use the same critical z-scores. I still construct the margin of error by taking the critical score times the standard error, and I still use my point estimate from the sample as the midpoint of my confidence interval. Alright, so let's try to do that let's do it. I don't know if I did that later or not. Let's do it now. The administrators of the hospital had 70 in their sample. And we know that the population mean is 280, and the population standard deviation is 14. And what we're trying to do is to estimate the mean for this hospital from the sample of 70 that we included here. So what was the sample mean? It was 275. And we want to construct a confidence interval for the hospital's gestation times based on this sample. Okay. Well, there's some conditions to check, which I'll show you in just a minute. As long as those conditions are satisfied, they're not going to be surprising. They're the same conditions we expect to see. Then I can build my confidence interval by taking my sample mean and adding or subtracting the margin of error. Margin of error comes from the critical score times the standard error, which is sigma over the square root of n. And I know both of those values. So what's my critical score? If I want 95%, 1.96. My n is 70. And my sigma, I don't know what the sigma is for the hospital, but I'm going to use the sigma from the population as a whole as the best estimate I have for that. So I'll use sigma equals 14. And then I can compute this as a margin of error. Quickly check what that'll be. 1.96 times 14 over the square root of 70. I get a margin of error of approximately 3.2797. There's more digits than that, but I'll keep those 4. That should be good enough. And so then my confidence interval is going to be in the midpoint, 275, plus or minus 3.2797. In particular, I am 95% confident that the true average gestation time for mothers at this hospital is between 271.73 and 278.28. In particular, that is below the population mean. So I am 95% confident that their value is below the population mean. In fact, I'm more confident than that because there's still a gap of an extra 2. I could choose a wider confidence level and still fall under the 280. Later, we'll learn how to do a hypothesis test. From this, can I conclude that their gestation time is less than 280? I'll go ahead and tell you that if the confidence interval does not include it, then yes, I can. And we'll see how that works, I guess, in 2 weeks at this point. All right. Now, before I start doing any of these things, I need to be able to check the conditions because I cannot use a normal distribution to construct my confidence interval if the normal distribution does not apply. That is, if the central limit theorem does not apply. So I have to check those conditions, and similar to what we saw before, the conditions I have to choose are the independence assumption and the 10% condition. Right, those are the only 2 things that I really need for the sampling distribution for means. Now, if I'm going to use the z-scores, I do have to have the population standard deviation, which is sigma. And for now, I'm just assuming that I have access to that for some reason. And in this case, maybe I have information about the overall human population. And so I'm just going to assume that that's the same standard deviation that applies to the population of mothers in this hospital, that they're not different from the rest of the world in that sense. What do these 2 conditions say? What does the independence assumption say here?
and randomized?
Okay, so what the independence assumption says is that one value in my sample compared to another value in my sample should be independent of each other. That having one value being a certain amount below the mean does not influence the probability of another value being a certain amount above or below the mean. If they are independent of each other, then each one is just a random choice, and it should then hopefully be representative. As always, it's very hard to get the independence assumption directly, because it's really hard to establish that each member of the sample is completely independent of the others. But if we use the randomization condition, we've collected our sample with sufficient randomization, we don't have any reason to suspect bias in our process or in our sampling frame, then we will assume that that randomization alone gives us enough independence to use this. So that's the randomization condition that we will treat as sufficient. What about the 10% condition?
That the sample size is 10% of the, at least 10% of the population?
Actually, the other way around. We want it to be no more than 10%
No more than,
of the whole population. And the reason is because, excuse me, this applies even if the population has a distribution that is not a normal distribution. If their distribution is, say, Poisson distributed, or if their distribution is uniformly distributed, or if it's exponentially distributed. It could be anything else. All sorts of different distributions. If I have the right sample size and I'm looking just at sample means, the essential limit theorem tells me it doesn't matter how the population itself is distributed, the sample means will be normally distributed. The problem is, if I have more than 10% of the population in my sample, and the population is not a normal distribution, then my sample means will actually start to look much more like the population than they will like independent samples. I have too much of the population really to have enough variability to see the normal distribution show up. I start to get pulled back towards the population's distribution, which may or may not be normal. And so the central limit theorem doesn't apply if I have too much of the population included. I want less than 10%. Now, in this example we were looking at here, if my sample size is 70, all I need is that there are more than 700 babies that are born in that hospital in that 6-month time period. That doesn't seem terribly hard to achieve, so I'm going to assume that that is satisfied here, and they randomly selected the 70, so the independence assumption, I will assume, is also satisfied. That allows me then to use the central limit theorem to construct those confidence intervals. Now what's interesting is if you play around with this, it turns out that to get this to work, I need my sample size to be big enough that I can conclude something of value, and it turns out it's usually at least 30. If I have 30 or more, then I'm usually pretty confident that I can use this. If I have too small of a sample size, there's not enough averaging going on for this sampling distribution to take hold as a normal distribution. So it turns out I need at least 30 to make that work. If I have less than 30, I still have ways to get around it. In fact, that's what we'll be talking about next week. That's one of the cases when we want to use a t-distribution instead of the normal distribution. Okay. Don't worry about that for now, but that will come up next week. If, however, I do have a sample size that works, and I have these conditions satisfied, then I know I can use the central limit theorem, and my sample means will be normally distributed with a mean equivalent to the true population mean, and a standard deviation equivalent to the population standard deviation, scaled down by the square root of the sample size, the square root of n. And so this is the distribution I'm using to construct those confidence intervals. Okay. That's what makes it all work. If I have the central limit theorem applying, which requires these two conditions as well as this sufficiently large condition, then I can use this distribution and figure out how many standard deviations above or below I need to go to collect the middle whatever percent confidence that I want among those sample means. Okay. So some terms you should know. I've already shown you these terms, so I'm not going to rewrite them, but I do want to emphasize their definitions here. When we did it with proportions, there was the standard error for proportions, standard error of sampling proportion in particular. that was calculated as the square root of p hat times q hat over n. That was the equivalent of standard deviation in the proportion sampling distribution. The standard error of the mean is sigma over the square root of n, and that is the standard error of the sampling distribution of sample means. It applies as long as I have a sample size that's at least 30, as long as I know the population standard deviation, and as long as I have these two conditions satisfied. Okay. So that's the standard error of the mean. The point estimate, that's what I see in my sample, is my best guess for the midpoint. That's going to be the midpoint of my confidence interval. In this case, that's the sample mean. I'm trying to estimate the population mean. My best initial individual guess is whatever I see as the mean in the sample. All right, that's my best guess. If I find a sample mean of 15, and I have to pick a single number to guess for the population, I'm going to guess 15, because that's the closest number I can think of to what it might be on either side. All right? That'll be the midpoint of my estimate, and then I want to widen from there to collect a certain amount of confidence, a certain region of the distribution of sample means. The critical z-score tells me how many standard errors I need to go away from that midpoint to collect the confidence level that I want. If I want 95% confidence, then I want to collect the middle 95% of all sample means, and that would be a z-score of 1.96. Right? If you check in your calculator between negative 1.96 and positive 1.96 on the standard normal curve, I find the middle 95% of all area. And then lastly, the margin of error tells me how far above and below that midpoint, that point estimate, that I want to go to collect that middle 95% of values. So I take my point estimate as the midpoint, here, point estimate as the midpoint, and then how far above and below that do I need to go to collect the middle, say 95%, if it's a 95% confidence interval, or the middle 90% if it's a 90% confidence interval. And just as happened with the proportions, I construct the margin of error by taking my critical value and multiplying it by my standard error. And that tells me how many standard deviations times the size of the standard deviations to collect the total margin of error. Questions about any of those terms? The key idea to remember here is the process is the same, even though some of the formulas are slightly different. You're always taking whatever you saw in the sample as your midpoint. You're taking your critical score times the standard error to get the margin of error, and you just add that margin of error to the midpoint to get the upper limit. Subtract that margin of error from the midpoint to get your lower limit. And that will be the confidence interval itself. The hard calculations can actually be done by Bognar or by Excel, for instance, or even by your TI. If you need to type in those values, it will do it for you. But it is important to understand what's going on, and so my recommendation is make sure you understand the formulas that we showed on those previous pieces of paper when we did the example. And also, when you use Bognar's calculator, I would encourage you to check that box that says to show the equations, because it will show you the equations, and it will also show you what values you plugged into each place. That way you can see how those pieces connect, and then later when you need to use them in a different way, you won't be able to necessarily use Bognar's calculator to go from a margin of error to a sample size, for instance. But you can recognize how to plug in the different pieces and then solve from there to find the answer that you need to find. So how do we construct the margin of error? We take the critical value and multiply it by our standard error. Again, the critical values are the same ones we saw before. For 90%, it's 1.645. For 95%, it's 1.96. And for other values, I'd recommend using Bognar's calculator exactly the way I showed you a moment ago to find those critical scores. And in fact, if you write down 80, 90, 95, and 98, I think you'll be able to do, well, 98% or so of all the confidence interval questions with those critical scores. However, it is important to know how to do the calculations, because I will warn you in the discussion next week when we do t-distributions, we will have a t-score, critical t-score. It's computed in exactly the same way, but it will be different for every single problem. You won't have one t-score that corresponds to 95%. You'll have a different one for each sample size. So you will have to be able to use the calculator to compute it. Make sure you understand how that works. I will show you how to do it when we need to in those situations. All right. We construct the margin of error then by taking the critical score, which tells us how many standard errors we need, times the size of the standard error. And the size of the standard error, again, is given by the formula sigma over the square root of n. So it's all here. This tells me how far above my midpoint and how far below my midpoint that my confidence interval must extend. Here's the formula. Now, use your point estimate, x bar as the center. You add the margin of error above it, subtract the margin of error below it to find the two endpoints, and then you can write it in any of those three forms. Okay, so this is the point estimate plus or minus margin of error form. I take my sample mean and I add or subtract whatever the calculated margin of error happens to be. I could also compute those two endpoints. If I take my sample one and subtract the margin of error, that's my lower limit. If I add my margin of error, that's my upper limit. So this is the interval notation for that. My sample mean, or my point estimate, minus the margin of error, up to my sample estimate plus the margin of error. And notice the total distance there is twice the margin of error. I could write the same thing in tri-inequality form. This basically says that I have 95% confidence that the true mean falls between these two values, or is in the interval described here. This is saying I have 95% confidence that the true mean is between x bar minus the margin of error and x bar plus the margin of error. And so once again, this is the same idea, but expressed as two inequalities written out, as opposed to as interval notation. This is what the textbook and the homework system call the tri-inequality form, TRI. It just means it's a three-part inequality. Any questions about those? Well, I already showed you how to do this example. With a 95% confidence level, if I use sigma equals 14 and my sample mean of 275, I can construct the confidence interval by computing first the standard error. 14 over the square root of 70, that's sigma over the square root of n. Comes out to about 1.677. You should keep more decimal places than I wrote here when you compute it. Don't round until the very end. Once I take that standard error, I need to multiply it by the critical score, which for 95% confidence is 1.96. That gives me the margin of error of 3.2797, which is exactly what I found when I did it on paper. And so my confidence interval is 275 plus or minus that margin of error. It's what I saw in the sample, plus or minus the margin of error that I computed. And as I said, that's 271.73 up to 278.27. Roughly. All right, well, what if I wanted to produce a 90% confidence interval for the mean birth weight of a U.S. baby born in 2018? Okay, well, what I could do is I could select a random sample, let's say of 64 babies in this case, find the mean in that sample, and use that to construct a confidence interval for the population distribution of birth weights. Okay. So let's do that. Let's see. I want a 90% confidence level. Right today. 90% confidence level. I want sample size of 64, and what I found in my sample is a mean of 3,500 grams. We're going to assume the population standard deviation is 400 grams. All right, this is just an assumption. I'd have to have some reason to back that up, but if that's valid, then I can use these pieces to construct a confidence interval. Now, before I do any work, I need to check those conditions. I need to check 3 total things. First, I need to check the independence assumption. Are my individual members of the sample independent of one another, at least with respect to the thing I'm measuring here, the birth weight? And I don't know for a fact that they are, but I know that I have a random sample of 64 babies, so I'm going to assume that that randomization gives me independence. So independence assumption, I'm going to say check by randomization. That's the first condition to check. The second condition to check, that's the 10% condition. What that says is I want my sample to be no larger than 10% of the population. Now here I'm estimating the average birth weight of a U.S. baby born in 2018, so I want 64 to be no more than 10% of all those babies. I feel pretty confident saying that 640 or more babies were born in the U.S. in 2018. So I'm pretty sure that this 64 is less than 10%, and that means that the 10% condition is satisfied. Basically 64 is less than 10% of all 2018 births. Okay. In the U.S. I should specify that's what the estimate here is for. The last condition is one I didn't write down, but I did state verbally. I need to make sure my sample size is large enough for this distribution to actually have enough flexibility and to actually see that normal distribution showing up. Because remember, the central limit theorem applies as the sample size grows. So I need it to be large enough for the sample size to follow that normal distribution. And in practice, I'm going to aim for at least 30. Okay? Sometimes I can't get that, and there are ways around it using the distribution we'll see next time. But here I want to make sure that my sample size is at least 30, and that's correct because 64 is bigger than 30. So since I have all 3 of those conditions, I do have the central limit theorem. And the central limit theorem tells me that the population, the sample means, will be normally distributed with a true value approaching the population mean and standard error equivalent to sigma over the square root of n. And from that, then I can produce my confidence interval. How do I produce my confidence intervals? Well, it's always going to be whatever I saw in the sample, plus or minus the margin of error. And remember, the margin of error is my critical z-score times my standard error, which in this case is sigma over the square root of n. I ran out of space on this page, so I'm just going to transfer some information over. I want a 90% confidence level, right? So what z critical value should I use?
.645.
Good. And I'm going to copy down the other pieces I know. N equals 64. X bar equals 3,500. I'm just going to assume this is grams. And sigma equals 400. So, if I'm going to produce my confidence interval, I need to compute my X bar and my margin of error. My margin of error comes from this formula. So my X bar is 3,500. My margin of error comes from Z star times my standard error. And what's the standard error here? Well, it's 400 over the square root of 64. Oh, I can see why I chose these numbers now. Square root of 64 is 8. So my standard error must be exactly 50. It doesn't usually work out that nicely, but happened to in this case because I made up the example. And my margin of error is my critical score times the standard error. So that's going to be the 1.645 times 50. What is that? My margin of error comes out to 82.25. And then lastly, the confidence interval is the estimate I got from the sample. That's my midpoint, plus or minus the margin of error, which is 82.25. So I could say that I am 90% confident that the average baby's birth weight in the U.S. in 2018 is 3,500 grams plus or minus 82.25 grams. Or another way to write that is that it's between 34, 11.75 grams and 3582.25 grams. If I wanted to write that as a tri-inequality, I would have the same two numbers. And that's less than what I'm trying to estimate here, which I guess I'd call it mu, population mean. So between 3411.75 and 3582.25 grams. And again, that is a 90% confidence interval. If I wanted to be more confident, I would have to make the interval wider. If I wanted to be a 95% confidence level instead, I use 1.96. That would mean I would be taking more standard errors. I get 1.96 times 50, which is almost 100. That would be 99 and change. So that would give me a wider window. I'd have a smaller lower limit and a larger upper limit. Not by a lot, but by a little bit. And that wider window gives me more confidence that I'm capturing the true value somewhere inside that interval. All right, let's check if that's in line. Excellent. So here's the solution on the slides. It looks like everything lines up. I did choose n equals 64 and sigma equals 400 because I wanted that standard error to be nice. Here the standard error worked out to be 50. And so my margin of error ended up being 82.25, and this is the number we found. Excellent. Any questions on that example or anything we've done with means so far? I just gave away the same idea. All that would happen is I would change the critical z-score. If I want a 95% confidence level instead of a 90% confidence level, I would need to take a higher number of standard errors. So my interval will widen. If I multiply everything out, it turns out, 98, I guess, was what it came out to. I estimated 99. It's 98. So I would have an interval between 3402 grams and 3598 grams. It's a slightly wider window, and I'm slightly more confident. I'm 95% confident instead of 90% confident that the true value is in that window, given my sample. This is emphasizing the proper way to interpret that. I recommend writing down this particular way of phrasing it. There are so many ways to inadvertently add an extra word or hedge on one part that will change the meaning of what you say. There are other ways to phrase this that are correct, but they're hard to capture without making a mistake in one place or another. So I recommend try to stick to exactly this phrasing. If I know my confidence level, I can say I am that percent confident that the mean, whatever it is I'm trying to estimate, is between my lower limit and my upper limit. So in this particular case, the interval I just produced, the 3402 to 3598, I am 95% confident that the mean birth rate of babies born in the U.S. in 2018 is between 3,402 grams and 3,598 grams. And we know how to compute these endpoints. They come from the confidence interval itself. This is the thing I'm trying to estimate, and this 95% came from the fact I produced a 95% confidence level. I could have done the same interpretation with a 90% one. I am 90% confident that the mean birth rate of babies is between 3411.75 grams and 3582.25 grams. Same idea, different confidence level and different endpoints, but exactly the same phrasing can apply. The only thing I need to change is how confident am I, what am I estimating, and what are the two bounds that I found for that estimate. So let's do one more example, and I think that will be a great place to end then at that point. Suppose we have the Human Resources Department of a large financial institution, large meaning it has more than 1,000 employees. You'll see why that matters in a moment. Wanted to know how long it takes their employees to get to work, so what are the average commute times? They randomly sampled 100 employees and find a mean travel time of 45 minutes in that sample. Suppose they assume the standard deviation for individual commute times is 30 minutes. Can we construct a 90% confidence interval for the average commute time for employees of this institution? Well, we should be able to. How do we do it? What do we do first? I guess that's the first question. Before I compute any confidence interval, I need to check that those three conditions apply. All right, does anyone remember the three conditions?
One is the 10% rule.
One of them is the 10% rule. What are the other two?
Independent assumption.
Independence assumption. And the third one?
Your sample has to be more than 30.
Right, I want my sample size to be at least 30. Technically 30 is okay, but I want it to be at least 30. Okay. All right, so let's check. Are those three things satisfied? First of all, do I have the independence assumption? Well, in most cases, we check for independence simply by checking have we randomized our sample. Is our sample used or collected with sufficient randomization? Hard to say, but when we're told that they randomly sample 100 employees, we're going to assume that that randomization takes that into account. And if so, then that randomization gives us enough confidence that we have the independence assumption. So we will conclude independence because of the randomization involved in the sample. What about the two sample size conditions? There's the 10% condition and the n at least 30 condition. N at least 30 is easy to check. What's my n value here? Yeah, they sampled 100 employees, so n equals 100. I need to make sure that that is, so that's more than 30. I also need to make sure that is no more than 10% of the thing I'm trying to estimate, of the population I'm trying to estimate. So I'm trying to estimate their entire workforce, more than 1,000, and I'm using a sample size 100. 100 is exactly 10% of 1,000, so if there are more than 1,000, then I'm just under that 10% level. Okay. Hopefully there's a lot more than 1,000 so that I'm not close. I don't have to worry too much about that. But if it's under 10%, we'll call that good enough. That means those three conditions are satisfied, so I can assume that the sampling distribution of sample means is normally distributed. That it will be centered around the true population mean, and that the standard error, the equivalent of standard deviation for the samples, will be sigma over the square root of n. That's what I want to be able to use. Alright, so now that I have those three conditions, I can use the central limit theorem. That means I can follow the procedure we had before for constructing those confidence intervals. Let's see how to do that. Have you help me out here. I'll write down the formulas. I know that my standard error for the mean is sigma over the square root of n. And I know that my margin of error is my critical score times sigma over the square root of n. And I also know that my confidence interval from that is my observed sample mean plus or minus the margin of error. Alright, so those are the three formulas I'll need to use. In order to evaluate these, I need to find sigma, n, z star, and x bar. Alright, so let's look back at the slides and see if we can collect those information. Let's see. I need a 90% confidence interval. So what does that tell me?
1.645.
That tells me my critical value is 1.645. That's because I want 90% confidence. My confidence level is 90%. I need a sigma. See, they're assuming a standard deviation for individual commute times of 30 minutes. So I'm going to assume sigma equals 30 minutes. I also need n and x bar. What's n?
Yeah.
Sorry, I missed that.
100.
Right. The 100 that are in my sample. N equals 100. And x bar, that's my sample mean. Says that I found in the sample 45 minutes as the sample mean. Alright, so these four pieces of information should allow me to evaluate each of these three formulas, and from that produce my confidence interval, and then of course interpret it correctly. So let's do that. Let's see, what's my standard error? It'll be 30 over the square root of 100. You can see why it shows 100 again. Square root of 100 is 10. So my standard error here worked out to be 3. I want to emphasize I chose these numbers to make this example a nice one so it would be easy to follow. But in practice, these are coming from real world data. These numbers are rarely going to be this nice. In fact, almost never. You'll usually find a decimal approximation that doesn't terminate, may not even repeat, so you're going to have to continue without rounding until the last step. In this case, it rounds nicely because it's an exact value. I have my standard error. From that, I can compute the margin of error. It's going to be my critical value times my standard error. And so that is 1.645 times 3. What is 1.645 times 3? 4.935. Again, in this case, I have equality. I'm not rounding because there are no more decimal places to worry about. But in practice, there will be more, so keep those in your calculator and use them in the next step. Now, once I have the margin of error, I can produce the confidence interval by taking my midpoint, which is whatever I found in the sample, 45 minutes, and adding or subtracting the margin of error, which is 4.935 minutes. Let me write this in the other form really quickly. 49.935 and 40.065. Yeah. Okay. So there's my two bounds for the confidence interval. How do I state this in words? How do I state the interpretation of this confidence interval? I am how confident?
%.
90% confidence level, so 90% confident. That the, here's where I have to think about what it is we're trying to estimate. Mean commute time for employees at that institution. If I know its name, I should probably state it, like Bank of America or whatever it might be. At that financial institution is between, now I write in my numbers, 40.065 minutes and 49.935 minutes.
It's recording.
This is the best way to write that interpretation in words. There's nothing incorrect in this statement, and it does summarize the full weight of what I can conclude here. Informally,
you cursed me.
What it means is, if I collected these samples over and over and over again, and I found this same value, 9 out of 10 times, the sample observations that I found would connect with a population value that is between these two bounds. The 10th time, however, it would just happen to fall outside of that range just by random luck. Sampling variability happened to not work out for me that time. And so for whatever reason, my sample gave me poor information. I felt like it was likely to be in here. I had that 90% confidence that it was, but 10% of the time, it ended up being incorrect. All right, any questions about that?